All right, so look at the front of your packet, the first slide. So raise your hand. What is that? Raise your hand. What is that a picture of? Got it? Yeah, we would call that an atom. So how do you know that's an atom? What told you that? Just have seen it before. It's kind of like
Jimmy Neutron.
Jimmy Neutron, yeah. Because there are neutrons in this diagram, which we'll learn about today. No. So we have to, before we actually get into sort of the details of the periodic table and chemistry, I'm going to talk first about something I think you're probably familiar with, and that is physical and chemical changes. Are you familiar with that? Oh, okay, I thought
Like
maybe
chemical
studied.
reactions.
Sort of. Yeah, so when we have matter, so let me start with saying this. Everything in the universe is either matter or
Nothing has matter.
air is matter. There's another class.
Dark matter?
No, that's matter.
True. It has matter.
Uh,
Tried. Anti-matter.
What about, what do I see here?
Matter.
Yes.
Plant.
Is the sun made of matter?
Yeah.
But what else
Fire.
does it release?
Radiation.
Very close.
Radiation. Yeah. Wait, did I have that right?
Radiation is a type of,
Matter.
light is a type of,
I know it, but I don't know.
Balthazar? Energy.
Oh.
So everything in the universe is either matter or energy. So we are talking about, in this unit, matter. Chemistry is the study of matter, changes in matter. And so you can change matter in lots of ways. Sometimes we change matter physically, or we can also change matter chemically. Okay? So when we have a physical change in matter, we have the same substance at the end of the chain. If I take an apple and bite it, and a piece of apple that comes off, is it still apple?
Yes.
Yeah. So that's only a physical change. There's no new substance formed.
Other than
If I take a piece of glass and break it, I still have little chunks of glass. That's a physical change. If I have an ice cube and it melts,
it's chemical.
is it?
Yeah, because it's turning into water.
And what is the ice cube made of?
Water. H2O.
It's the same substance. So changes of state of matter, boiling something, freezing something, melting something, those are physical changes. You're still in the same substance. But there are other changes that we call chemical changes, which actually result in a new type of material being formed. It's no longer the same substance. For example, you get a nail made of iron and it rusts. That is a chemical change. That rust is a different material than the iron that you started off with, it's iron oxide. Burning something. You take a piece of paper and burn it in your fireplace. You're changing that paper into what? Some of it is shaped, some of the molecules that made up that paper are released as carbon dioxide, carbon monoxide. Okay? Some of it is left over, most of the carbon, much of the carbon in the ash of that paper, but it's changed into a new substance. No longer the same material. When I take a bite of this apple, what's happening inside of my stomach and small intestine? Is that a chemical change? Yeah, my enzymes and acids in my stomach are breaking this apple into simpler compounds, into basic sugar and carbohydrates. It's not the same substance. So, some clues that a physical reaction is taking place It's just a change in the phase of matter from solid to liquid or liquid to gas. Gas to liquid. If you take some salt and you put it in water and it dissolves, that's actually still a physical change. The salt is still there. It's disappearing because it's breaking into very small pieces, but it's still salt. Change in the size of the material. Clues that chemical changes are taking place. Changes in color. Bubbles form. Smoke is released. Those are some signs that a chemical change is taking place. Think of rusting or burning the paper. You trying to conduct a physical change on that pencil wax?
He was like, oh, the fence. That sounded so weird. It was supposed to look at so bad. Did you guys have to go take
If you saw smoke coming out of my ears, because I was very angry, what type of change would that likely indicate? Chemical change. Luckily, you don't see that right now, right, Wyatt?
He just put it in your table.
All right. Raise your hand if you want to tell me, what kind of changes are these? Burning a piece of paper, Emma, chemical. Smashing a soda can on someone's head would be an example of what type of change, Olivia? Physical change. Lighting magnesium and having it burn in someone's chair that they're about to sit down on.
Sit down, Wyatt.
Jack? That'd be chemical change. Mixing vinegar and baking soda and pouring it into someone's mouth would be an example of what, Layla? Chemical. Throwing somebody into a snowbank and then the snow subsequently starts to melt. Wyatt, what type of change would that be? Physical.
What the chemical sugars are now happy?
I don't know. Fireworks going on.
Physical. Chemical.
All right, who's confident in answering can explain? Jake, why are you saying physical?
Because it's just changing the way it falls out and different stuff.
Danielle, you have a.
It's chemical because it's fireworks. Lights up, goes up in the air, blows up. It's like
There's smoke, things are burning, colors are produced. That is a chemical reaction. You're not frying an egg.
no, smoke and still there.
Is what you have after you fry the egg the same thing?
No. Yes.
No. That is a chemical change. Cooking things is a chemical change.
It's just wait.
There's bubbles for. Is there a change? Is there a change in color? The egg white goes from
It's still white.
white to, it goes from clearish to white. That's a chemical change. Digesting food in your stomach. Chemical.
Are more things chemical?
No, it just depends on what you. Sorry, no. Dissolving sugar in water.
Physical.
Physical. Boiling a pot of water.
Physical.
I'm hearing both. Raise your hand if you're confident and tell me why, Maddie.
Chemical because there's bubbles.
Okay, well, there are bubbles forming, but those were hints, not rules. So I see why you said that, Maddie. That makes sense. I'm glad you brought that up. Jake?
First of all, you said 5 minutes ago that it's physical, and it's the same thing with the ice cube and the belts. It's still the same substance.
Yeah, what is boiling water doing?
It's putting oxygen in it.
No. And it's changing
It's separating
a liquid
into gas.
into a gas. That's
Hold on.
a physical change.
But it's chemical because up here I clues that a chemical in a bubble.
Those are clues, those are not rules. So that's an activity where there are bubbles formed, but those bubbles are actually due to hot water rising in the boiling hot water. Another hint that we sometimes you might hear is that physical changes can be undone and chemical changes can't. That's not really a great one though, so I don't include it on the list. Can you turn a fried egg back into a raw egg? Can you take liquid water, turn it back into ice? Yeah. So
But
those
you
are,
can turn when you burn something, like you said, when you boil water, it can turn.
that's a physical change. All right.
I had something with the building.
That's a science question.
No, it's actually gotta do.
Okay, ask after class. Kid.
You ready?
Yeah, I'm gonna go viral.
I'm ready.
All right. Let's talk about some definitions here. So, we talked about a few of these things in the beta class, but we didn't talk about atoms. So an atom, that thing you saw, that's kind of a model of an atom. How could you define an atom? You want to know? Small particle? Yeah?
Large power source?
Oh, because of like giving atomic power, like nuclear energy, it can provide energy. You know? It's like a building block. Yeah, all matter is made of atoms. All matter is made of many, many atoms. They're the building blocks of all matter. And they're made of even smaller pieces. An atom is very, very tiny. You can't even really see an atom in a microscope. So they're very small, but they're actually made of even smaller parts that we're going to learn about. They're called protons, neutrons, and electrons.
Neutron.
What's that? Well, we can, in a very, very powerful electron microscope, we can sort of see atoms. And through experimentation, scientists have learned how an atom is sort of built. Like that diagram you saw in the very first slide, that is one model of an atom. It's actually not really that accurate. We'll talk about why a little later on. So atoms are the building blocks of matter. They're made of protons, neutrons, and electrons. Elements are pure substances. Substances that cannot be separated into smaller substances. What's that?
Like it's like above element.
I'm not sure what your question
It's
is.
not element.
So gold is an element. It is made of nothing other than gold atoms. All right, so these terms we haven't talked about. What is a compound? Two.
Element.
Yes, if we have a combination of two or more elements, we can form a compound. Two or more elements bonded together form a compound. Carbon dioxide is a compound. What's it made of? Carbon and oxygen. Okay, so then we have this term of molecule. If you took some carbon dioxide gas that's in this atmosphere, and I split it into two groups, I would still have carbon dioxide. Could I do that forever? Could I keep splitting it, get smaller and smaller and smaller? No. Eventually I would end up with the smallest piece of carbon dioxide I could possibly have. If I took that smallest piece of carbon dioxide and split it again, what would I end up with? Carbon and oxygen. That smallest piece of carbon dioxide is what we call a molecule. Right? A single molecule of carbon dioxide. And that carbon dioxide molecule, it's still carbon dioxide. It still has the properties of carbon dioxide. But if I were to break that molecule into its components, it would no longer be carbon dioxide. It would be something else. So let's use some of these terms that we just defined. Hydrogen has the symbol H and oxygen symbol O. They are both what? Yeah? They're both elements. Think about this next sentence. When two blank of hydrogen and one atom of oxygen combine, they form one blank of the blank water. Anyone think they understand these words enough to make that into an actual sentence? Mitchell? Two molecules of hydrogen? Disagree? Disagreement. Sophia? Two atoms of hydrogen, one atom of oxygen combined? They form one molecule of the compound water. What is the smallest piece of silver that you could have? No. No. Yes, one atom. What's the smallest amount of water you could have? There is no atom of water. There's only a molecule of water. What is the smallest amount of glucose you could have? One molecule of glucose. What if you split that molecule of glucose? What would you end up with? What element? Several atoms of hydrogen, oxygen, and carbon. Remember C6, H12, O6, carbon, hydrogen, and oxygen. All right. Yes. We're going to talk a lot about that when we get to our nuclear. So I won't answer now, but we will know the answer eventually. So, as I said, an atom is actually made of even smaller pieces. An atom is really small, but it's even made of smaller pieces called subatomic particles. So, there's three types that we'll talk about. So this is, you're familiar with this model of the atom. We have a name for this little cluster in the middle. The nucleus. But it's different than the nucleus of a cell, because this is not living. This is just an atom. It's non-living material. It's called the nucleus. In the nucleus, there's two types of subatomic particles. They're called protons and neutrons. Neutrons are made of neutrons.
Really? What is all these lost cousin Jimmy protons?
I don't know. And so protons are these very small particles found in the nucleus. And these subatomic particles can have a charge as well, an electrical charge. Protons, can you guess what charge that is?
Positive.
Positive charge. Also found in the nucleus, in this center area of the atom, is a second type of subatomic particle, the neutron. Can you guess what its charge is?
Negative.
No, that's what everyone always wants to say.
Neutral.
Neutral. They have no charge. They're neutral. That's why they call them neutron.
No charge.
Then there is the third subatomic particle, which are around the nucleus. When we see these things, they don't really move around the nucleus like that, but Oh, that's okay. We'll talk about why that is in a minute or another time. So those are electrons. Can you guess their charge? They have a negative charge. So protons and neutrons in the nucleus, and then electrons outside of the nucleus. You guys done? Yeah, we'll watch that at the end maybe. Because we got to talk about periodic table. Hey, I have a special gift for you. Your very own copy of the periodic table of elements.
I want it. Give me it. Are we gonna have
Yay! All right. So the periodic table of the elements is this chart. You've probably seen it before somewhere. I think there's a copy in your agenda or something like that. You have a poster in your room of it. Yeah, it looks like that, you know. I think it's weird that I have a poster of the periodic table in my house. What, you don't have it? All right. So the periodic table is this chart. It lists every element known to humanity. It was developed actually in the 1800s, not in this exact form, because scientists didn't know about all the elements at that time. Developed by a Russian scientist, Dmitry Mendeleev, in the middle of the 1800s. And the periodic table lists all of the elements, and they're put in a specific order and arranged in a certain way. That's really important. So as you read the periodic table, you read sort of, you could go in one row, left to right. And what you'll see is there's a whole number, and each periodic table entry, there's a whole number at the bottom. Okay. And from left to right, what happens to those numbers? Okay. They increase by 1 each time. That is called the atomic number.
That's not dangerous there?
No.
How many atoms they have?
Nope.
What?
We'll talk about it. So the rows of this periodic table, they're called periods. Okay? And we'll talk about everything in one row has the same number of electron shells. The columns of the periodic table are called families or sometimes groups. And elements in one column, in one group, typically have similar properties. In the periodic table entry for each element, there's a name of the element and a symbol. For example, hydrogen is just a capital H. Sometimes the symbols are a single capital letter, like hydrogen, oxygen, carbon. Other times, if they're two letters, it's a capital letter and a lowercase letter. Yeah. Hydrogen is the top left, helium is the top right.
Saying the periodic table.
What?
Why is there a lot?
Yeah, their songs help you memorize them. No, you don't have to memorize them. All right, so if you look at the periodic table, there's some other numbers as well. At the top of each periodic table entry, there is a longer decimal number. That's called its atomic mass. We'll talk about what that means. So these atoms are really small. Obviously, they're extremely small. And so to measure the mass of a single atom, scientists actually had to come up with a new unit for it. You couldn't use milligrams or micrograms or nanograms even. So the unit they've come up with is called the AMU, the atomic mass unit. And so in this system, the mass of a proton is 1 AMU. The mass of a neutron, also 1 AMU. The mass of an electron? 1. It's actually 0. It's technically not 0. It's so small, however, that we basically ignore the mass of the electron.
It's so sad. Just ignoring the electron.
So let's talk about how we use the periodic table. This is what you're going to have to do in your homework. Most of the time, you're going to be referring to the two main numbers in the periodic table entry, the atomic number and the atomic mass. So this is the periodic table entry for carbon. Symbol C. Atomic number 6. Atomic mass 12.01. The atomic number here, the whole number, what it's telling you is how many protons there are in one atom of carbon. So carbon has 6 protons. This is what determines what element. All carbon has 6 protons. That's the definition of carbon. What if something had 7 protons? Would it still be carbon?
No.
What would it be? It would be nitrogen. Nitrogen has atomic number of 7. No two elements have the same atomic number. And typically, atoms are neutral in their charge. So if it has 6 protons in it, how many electrons does it have? Also 6. And that would make its charge neutral. So carbon has 6 protons, it has 6 neutrons. Atomic mass tells us the total mass of one atom. So, what's the mass of a proton? 1. A neutron? 1. So, if it has 6 protons, how many neutrons do you think carbon has?
6.
Right, to give it a mass of 12.01.
Oh. What is that?
Yeah, we'll talk about that. Okay, good question. So basically, atomic mass is the total number of protons and neutrons found in an atom. Yeah, we'll talk about those numbers at the bottom. It's a series of numbers separated by dashes. It's called the electron configuration. We'll learn what that means eventually. All right. Here. We'll finish this slide, and then you'll be able to do your homework. So, what you're going to have to do in your homework mostly is figure out how many protons, neutrons, and electrons various elements have. So let's look at how to do that. So look at oxygen on this chart. Who could tell me how many protons does oxygen have? Olivia. How many electrons? Raise your hand, please, for these questions. Devin? Also 8, because they're going to be the same. How about neutrons?
Oh, 0.9.
Hold on, no. Jake? 8. Why 8? It's not always the same. It is in this case. To find out the number of neutrons, look at this. Take the atomic mass and round it, and subtract the atomic number. So the atomic mass is 15.9994, which rounds to 16, minus the number of protons, 8.
I get it.
Yeah, how about fluorine? Number of protons? Sophia? 9. Number of electrons? Number of neutrons? 10. So now we have an element that has a number of neutrons different. How did we get, who could tell me, how did we get 10, Danielle?
Because you round 18.9994 to 9 to subtract 9, you get 10.
Good. All right, let's finish up with these two. Gold. 79. 79.
118.
118. How about helium? 2. Yeah, no, you just round. We'll talk about why they are decimals tomorrow.